So this is a session on regression for those who are interested. But before I begin, let me tell you that this is simply an introductory session. Clearly you will find more explanations in our book, which is also an introductory exposition of possible models that one may consider whenever we are interested in doing post-estimation analysis with the Alkire and Foster measures. So to begin, this is chapter 10 of our book, just released in June 2015. Joint work with my colleagues. And you can find the chapter as it is on the OFI website as a working paper, but you can also download the chapter, and also you have other resources like Stata-Do files on the multidimensional.org website where the book is basically presented. So to begin here, I think it would be interesting for all of us to summarize all the things, analysis, and descriptions we have learned up to now. So who would like to give me an overview of where we are? Just to have an understanding of why do we really need to regress? Clearly coming from a field which has been my field, I am unbiased. I like to regress always. But it's not necessarily the case. Sometimes we may not need regressions. So the question that first comes, I think, is basically to understand why we need to regress. So for that, who would like to give me a brief overview of what we have learned over this, maybe basically a week and a half? Here is written, but who would like to give me an overview? What we have done, we began with what? Yes?
Yeah, so I think we met last Monday to start from a normative perspective, to think about why we are constructing this stuff, why we are thinking about multidimensional poverty. And then we went into some of the math underlying this, looking into censored head counts, uncensored head counts, to better understand how to translate the data into the concepts we had discussed earlier on. And in here we also looked into poverty in itself, but also the depth of poverty or the number of deprivations. Mm-hmm. Then later on, the idea of breaking it down by gender, breaking it down by regions, to see how subgroups of the population of the sample look like, and how their deprivations contribute to overall deprivations in the country. And then a little bit of sensitivity analysis related to the construction of the index. So what about the validity of the dimensions we are using, if there are maybe results driven by the construction of the index itself. So we looked into associations, into redundancies, and so on. And then what you would summarize as robustness of parameter selection. So as we have discussed in detail by now, that there are certain choices we have to take related to poverty cutoffs, to weights, to all kind of issues, which go beyond normative decisions, but also involve technical decisions. And in here, the robustness plays an important role. And also the standard errors, especially when we want to compare across different groups in the population. So to basically see if rural areas are more affected than urban areas, or if country A is more affected than country B. And then testing hypotheses related to the trend or related to the incidence or intensity of multidimensional poverty. And okay.
And finally,
that was more or less what we looked into yesterday, how we could maybe extend this measure to a multi-period space, looking not just into 1 year, but looking into 4 years, 5 years, and understand multidimensional poverty as something where people are deprived not just in different dimensions, but also in different time periods.
Okay, thank you. Anyone else has something else to say? Maybe up here, or it's like a comprehensive overview, right? So essentially this is it. We have done all this analysis. We have our measure. We learned the HA by group. We broke down by dimension to see which indicators contributed most. We also looked at associations and redundancy, trying to assess in what extent we can really be sure that our indicators are really measuring different aspects, maybe not really, and if that's the case, how can we account for that in the design of our measure? We then moved on to analysis based on the robustness, just to see in what extent our choices, the K value, the Z values, the weights, are really affecting the numbers that we are getting. Then we moved on to these standard errors and statistical inference, because we clearly want to say in what extent poverty has decreased, or clearly poverty is different across population subgroups. And the only way to do it is basically to test. And today and yesterday, we also looked at the analysis of distribution, which is inequality among the poor, just in the lecture before, and dynamics over time, where we want to assess whenever we have data for different time periods, whether it is cross-section, different cross-sections, or maybe the same person or the household followed over time with a panel. So this is all we have done up to now, which is a lot. So this is the outline of the chapter of the book, which is essentially a description of the types of things we can think of. But I would like to skip that part and then look at this table. So the question is, what are we missing? Are we really missing anything or not? We have done many analyses, many of them, by groups, by indicators. So the question is, are we still missing something?
We didn't study causality.
We didn't study causality, that's very good. So if someone plots a table like this one, what is the kind of information that you can retrieve from this table? Look at this table here, which is coming from a paper with Mauricio that we began in 2013, which is now a report of 100 pages. The paper, it is a very complete one, using the Indonesian Family Life Survey data set. This time, this is for 1993. So I'm illustrating just a simple table. We have computed the N0 for Indonesia, and it was using 5 dimensions with different indicators. And we got this number, 0.13, an index for the whole country in 1993. So here we were interested in just trying to understand this 0.33, right, here, this one. And then we plot the value of the N0 for poor households, clearly, in terms of the characteristics of the household head. So we knew, and we still know, that for this year, and for our sample, the average years of education of the household head is 2.1. The average age is 25 years old, and the household size is around 5 people average. We also have the proportion in terms of the religion, and this is across different districts. 80% were Muslim, and 91%, sorry, and 80% were male-headed. So this is information which is also trying to explain what is happening with this M0. No? But what is the situation here? I mean, we are trying to explain, no? But descriptively. We are still not in a modeling framework. As you were clearly saying, we are not assuming any causation. We are not saying these variables are affecting or explaining M0. We're only trying to understand what is behind this index. No? So the issue here, I wouldn't really call it an issue, but it is that the situation is that we have this information, which is in a certain way reaching itself, but it remains partial, because it's still bivariate or univariate. We are still looking at each of these factors separately behind this M0. So we need a technique, we need something that can put together this information in a single framework, but at the same time can also account for the effect or the size of each of these variables when explaining M0. So we need regression. This is essentially the intuition behind. Whenever we are moving from the descriptive world, which is clearly already reached, as we have clearly summarized, we need something else. We move to the inferential part, so we need a model. Despite whenever we interpret the coefficients of a model sometimes as correlations, we always need to remember that whenever we have a regression, whenever we have a model, we are imposing causality. So even though we don't want to say this is causing this, it is the case. So we need to remember that we are making a choice again on what types of relationships we are interested in studying. why we are having M0 in this case as the dependent variable, and why we are having these variables as possible explanatory variables. So this is basically the motivation. So now the question is, why is this important? Well, we know we are trying to explain things, but why is this important? Yes?
I think that we are studying poverty because we want to reduce it,
Mm-hmm.
and then we need to understand where as you say, where the causes of poverty and how can we change it, so the regressions models can help us to understand how these dynamics work.
Okay, so this basically trying to assess the transmission mechanisms behind poverty, right? And the different factors behind. So there's two types of ways of seeing regressions. You know? One is simply to have like a reduced form, which is the one that I'm going to explain here. And the other way, which is I would say the proper way to do it, is to model the relationships across different indicators in a more general framework, right? These generalized equilibrium models, does this tell something to anyone? Well, it's generalized equilibrium, which we learn in economics, is basically that for each sector of the economy, we try to model what is happening across trade, across deficit, fiscal deficit, across monetary decisions, fiscal decisions. Everything is modeled by sector. And then we end up having like a sort of relationships across variables, which clearly we know where they are coming from. But what I'm going to explain here is very simple. It is what is called a reduced form regression, which is essentially saying, well, I have a dependent variable, and I want to find some factors that can attempt to explain this dependent variable.
The dependent variable itself has been constructed by taking some of the factors which you already might consider in the
Exactly. So that would lead to what is often happens, a potential endogeneity problem
Yes.
that needs to be dealt with in a regression, which is clearly the main issue in this type of models. So what I'm going to illustrate is an illustration. I'm going to give you an example how to think about it. And then it would be you afterwards, depending on the measure that you have constructed, to think about what are the potential factors on the right-hand side of the equation. Mm-hmm. Okay, so these regressions could be framed into two different groups. We could think them as micro-regressions or as micro-regressions. Again, I'm building here on what is in economics we often use called micro or macro, right? So a micro-regression, intuitively, would be more or less what kind of regression? Something at the household level or something at the individual level, right? And a macro regression would be something aggregated, right? Provinces of a country, or maybe countries themselves, or some other group, could be maybe religions, different types of religions. The problem clearly comes whenever you have different types of religions. We don't have, I think, so many in the world. We will have we have not really number of groups which are enough to do a regression. But it's also possible to address that in a sample selection problem whenever we have small observations. But let's consider the case where we are just thinking about spatial aggregates, like provinces, districts, or countries, and we have enough variability. Okay? So these are the two types of regressions we can think of. Then would be basically the type of questions that we may address with these regressions. In a micro-regression, what kinds of economic or maybe socioeconomic questions we may be interested in studying? If we are thinking about explaining poverty of a household or poverty of the individual, what would be the main question behind that regression?
Determinants.
For example, we could have also poverty profiles, right? We'd like to have poverty profiles. In the macro regression case, what would be a model interested to be studied if you have the M0 by province as the dependent variable? What would you have on the right-hand side? Again, from a reduced form perspective. GDP, for example. So that would lead to a model where the parameter associated would be more or less something like an elasticity. I'm saying like an elasticity. So you could have a model in terms of elasticities, trying to address the sensitivity of GDP, or maybe the gross national product, to poverty, right? So those are potential things you can think of. Maybe the effect of a policy also. We may be interested in assessing, a trade policy how a trade policy can affect multidimensional poverty, the M0 across provinces of a country. Okay? So those are potential questions that we could explore. So in this lecture, and clearly this is the purpose of the chapter, we will provide you with a general modeling framework for analyzing the determinants. So these variables on the right-hand side of the equation, I will call them determinants, which means like causal factors, but not really in a strong way, rather in a weak way, in a weak sense. Of the Alkire and Foster measures, both, we could think about micro and macro levels of analysis. The modeling framework is studied within the class of what's called generalized linear models. Okay, so this is a fancy name. But if you look at it, it says linear models, basically, and then we are adding generalized on top. Why do we need GLMs to study these things? And clear we have here the explanation, but how familiar are you with linear regression?
Well, because potentially we have heteroscedastic errors range for linear.
Okay, but heteroscedasticity could also be addressed in a linear model,
Yeah.
right? So linear regression, how familiar are we? Not much, more or less? Yes. So I'm going to explain later on, but maybe it would be useful to see it now. Okay? So this is a linear model. Okay? We have a dependent variable here, which we often denote by y. And in a linear regression, we are interested in explaining this y in terms of some deterministic, what we call component, and some error component. Okay? So this part, which is the part that's trying to explain this dependent variable, is basically the conditional distribution of the variable given the explanatory variables. So it's a more, if you want, it's a more abstract way of understanding it. Okay? So here among these x's we could have, let's think about y in terms of consumption. If we're interested in explaining the consumption of a household, so that would be our variable here, we may have some explanatory variables, maybe the household size, maybe, I don't know, what else could explain consumption of a household?
Income.
But the consumption is basically income. So that's what I'm having as a dependent variable. How can I explain the income or consumption of a household? What factors would you include there? Household size, age of the household head, the education of the household head. So there may be sociodemographics associated with the household head. So those would be our x's there, right? So in a linear regression, it means that we are having a line to explain this relationship. And whatever we are not able to capture by these explanatory variables will remain in the disturbance part, which is called the error component, right? So is this more or less clear, what we're having? So this part is the part that explains clearly why, and this is the part that we are not able to explain, because we are not able to capture all the explanatory variables here, because we don't know them maybe. Clearly we try to have this as small as possible. So this is a linear regression. No? But clearly a linear regression only holds under certain assumptions, right? When would be a line the appropriate way to assess the quality of it? Because with a line, with this linear regression, imagine you have your data set, right? This variable, which is the logarithm of consumption. And let's say we are trying to explain that by the years of education of the household head. So we would have like a scatter plot, more or less in this way, right? So this is our dependent variable, and let's say this is years of education of the household head, which is positive, and here we have the consumption, right? So we may have a scatter plot like this that will tell us as the years of education of the household head increase, well, the consumption of the household will also increase, right? Let's try to have something like this. So this is our observations, right? So this is our plot. In a linear regression way, what we are trying to say is, well, we try to assess this relationship, well, by fitting a line. So that's what we want, a line. This is the linear regression model, the line. Okay? So clearly this holds whenever this variable is what type? Cardinal or continuous, right? If we have a variable that takes on only two values, which is our case in this world of counting deprived, non-deprived, poor, non-poor, Does a line will make sense? No, right? So we cannot really fit a linear model in these cases. We have a line here, and this is what we are representing in this simple equation. What we are trying to say is this is the conditional expectation, and whatever we are unable to explain is in these disturbances. So for each observation, this is the disturbance, right? So in a standard way, what we try to find are the parameters associated with this line, right? Which is basically what? How would you represent this line?
You have a 0.
It will have like an intercept, and then it will have a slope associated with variable 1, right? Here we have that. Right, that would be our regression. So we want to get estimates of this and estimates of this, which is max mean estimates, right? So the estimate of the slope and the estimate of the intercept. How do we do that? Well, we use a technique we call ordinary least squares. Essentially, we minimize the distance between each observation and the line we are trying to predict. That's it. We minimize that and we get these parameters. That's how it works in the simplest case with one variable. So now we know that in the case of the deprivation and clearly poverty here, we cannot have a line because y will take on only two values, either it's poor or non-poor, or what other type of dependent variable we can use at the micro level from those that we have learned here. We can either have a dichotomous variable, like in our data set, that tells us each person is poor or non-poor. No? What else can we use as the input variable there? What? Okay. What else? What is the key thing that you use to compute poverty? The C vector, the score vector, sensor, no? Sensor deprivation score vector. Everything is computed on the basis of the C, right? So you could have the score vector also as a dependent variable there. Is the score vector something between minus infinity and plus infinity?
No.
What are the values that the score vector will take?
0, 1, 2, 3, 4.
You could either be non-poor, which is the uncensored one, non-poor, or poor, and then you would have the values, no, that you take of your weighted deprivation. For those that you censor, clearly the sensor deprivation score will not take the value of 0, right? We are only looking at those who are poor, so that have a deprivation score which is greater or equal to our K threshold. So the lower bound of the C is how much? K, right? K. And it will go up to 100, up to 1, right? So it is bounded. It's not really purely continuous, but it's a bounded variable between K and 1. So for this reason, we cannot just use linear models like this one. We need something else. And this something else is called a generalized linear model. Yes?
And it's also cardinal, not continuous.
In addition to that, it's cardinal. It means that it will may be discrete at some extent, right? More or less like consumption. Consumption is not purely continuous either. So maybe cardinality may not be an issue, but the bounds, yes, cannot be negative, right? So we need something else, and this something else is called the generalized linear model. So before I move on, this is the notation we are using. This conditional expectation, which is the one that we had before here, right? We model it, like in this simple case, using one intercept and then a combination of the slopes, if you want partial slopes, of each variable, right? And then we write a model like this in a very simple way. So this is the linear model. And what we need is something which is a function of that linear model. And this is called the generalized linear model. So look at the equation now. What is happening?
You want me to do?
There's something that has disappeared.
Yeah.
What part?
Epsilon.
The epsilon,
Yeah.
right? So the error component is not there anymore, right? We are only having a function of the conditional expectation, which is G. This function will do something such that we will get a linear form. Okay? So it's called this link function, this thing. it will transform, I think this is the one, it will transform this such that we have a linear form, right? In the linear case, the value of this g function is how much? G of this. G of this. How much?
Equal to C, I think.
It will be equal to 1, to the identity function. Look at it. It's g of this. In the linear case, g is the identity function. It's like saying having a 1. G is 1. But now we are having things that are non-linear. And this is the case where we have here. And in addition, we don't have the disturbance. So where is the random part? Because before, here, the random part is in this part, right? Because we are conditioning here by x, so it's not random anymore. One condition is non-random. So this is the random part. We don't have a random part there. Where's the random part?
X.
What do we do to assess the random part of it in these models? What can we do?
You see.
We need to assume something else. Have we talked about the type of distribution of the dependent variable and of the disturbance before? Have we really considered whether these errors there are normally distributed or distributed according to something else? Not really, right? So in the linear case, because we are just plotting a line, we don't really need to assume a specific type of distribution for the disturbance, where is the random part of our model. Often we assume normality because we need to do inference and then things come from the asymptotic normal theory, okay? But that's not the purpose now. We have moved to a situation where the random part is not visible anymore. So to account for the random part, we need to give a distribution to the dependent variable. So those are the main two differences between the linear model and the generalized linear model. In the generalized linear case, we are forced, if you want, to give a distribution to the dependent variable, because otherwise the random part is not possible to account it. And the second difference is that we are modeling a function of the conditional expectation instead of having the conditional expectation itself. Clearly, this generalized linear model has the linear model as a specific case, where G is equal to the identity function and where the disturbance is normally distributed. Okay? Is this clear? Yes?
I have one question. You say that in micro regression, if I will take in multidimensional part as a dependent variable.
Yes.
So I want to do regress, but then what are the explanatory variables you suggest?
That's coming in the example. For now, we are just on the method. Just
because
run.
no, what I am thinking is you have already taken income, you have taken health, you have taken education.
Yeah.
So three major domain determinants of
Yeah.
basic idea is to look out the determinants of poverty.
Yes.
So we have taken it out.
Yes.
So and how good it will be? So we cannot use it as our
Yes.
variables.
Yes.
Then what remains for regression?
That's a good question. What remains for regression? That's the key issue here. What do we have? And there's possible answers for the question. But before we move on to that, let me just ask if everyone is clear with this G.
I have a question about, like, you are assuming this distribution of...
We are assuming distributions, and this is the
How
type
do you
of distribution.
choose?
How do we choose?
Yeah, how do you choose?
I'm going to explain that. But is this transformation from the linear to the G clear? Yes or no?
Yes. Actually,
For whom is not clear? There?
Actually, there is a confusion. Actually, in the textbook, classical linear regression model and generalized linear regression model, the distinction between these two made on the basis of the characteristic of the disturbance star. In case of classical linear regression model, disturbance star moves characteristic and non-correlated.
can happen.
But in case of generalized linear regression model, the regression model is generalized because the disturbance star not follows these restricted assumptions.
Yes, that's
But
also
here
that's something that follows from the definition. Let me write the thing, okay?
Yes.
And then we can go back to what you were pointing out. So let's have the linear model first. which we know is the expected value of y given the explanatory variables plus a disturbance. And this applies for a sample, right, over n. So this is our linear model. What are the assumptions of the linear model?
Assumption there linear relationship between dependent and independent variable, and other is the disturbance term is homoscedastic.
Okay, let me just write down the example we have. What we said is that this is this, right, in the linear model. Right? So what you are, the assumptions that you are describing are those that correspond to the normal linear model. So this is the linear model. Now I can talk about the normal linear model. Okay? The standard linear model assumes that the disturbances that you were just saying are homoscedastic. Homoscedastic, clear for everyone? No. Homoscedastic refers to the properties of the disturbance. We are assuming now here the disturbance has all the information that we are not able to explain with this x variable. Okay? All the information. If you want, this is specific for each person. So now comes the question. How do we assess this specificity? The variance and the mean of the disturbance will give us some information. Homoscedasticity supposes that the variance of each person is the same. That's why it's called homoscedastic. So that's the main assumption. We assume that the variance of each person is the same. But clearly, in reality, it's not the case. So we have a problem of heteroscedasticity, which means that the variance of each person varies. Whenever we have that, the standard linear estimator that I just explained, which is the OLS, needs to be corrected for that. And we have a correction there, which is the weighted least squares estimate. So that's one thing. The other is that we didn't talk about the distribution of the random particles. Right? The normal linear model assumes that this distribution, that is, these disturbances, are normally distributed. Normal distribution. Is this clear to anyone?
Yes.
No? The normal distribution is a distribution that has a form like a bell. More or less like this.
Mean median model.
Okay? And the properties of this distribution say that the median, the standardized normal, and let's say that this, the mean, the median, and the mode all coincide. And it's a very nice distribution because it's also a symmetric distribution, which means that 50% of the observations are on the right and 50% on the left. So all the statistics that we have been studying with this data command are always compared with regards to the normal distribution. We want to know how asymmetric we are, to the left or to the right, and also how much information we have in the tails and in the peak. So this is the kurtosis information that comes from the distribution. This normal distribution has a kurtosis of 3. And we compare the kurtosis of an alternative distribution, let's call it something like this, with this one. So in the one that I just drew, we have more information in the tails compared to the peak. So that would be like a flat one. Okay? So that will give you a different number. Why is this important? Because in different situations, you may want to assess in what extent the probability of happening extreme events is higher or lower. So if you have more information in the tails, the probability is higher. Right? So this is the normal distribution. And that's what we assume here for the disturbance in the normal linear model. Okay? So this is the linear model. What I'm talking about here now is about a generalization of this linear model, which holds whenever this dependent variable is continuous and can take any value from -infinity to +infinity, which is not our case with the dependent variables that we have for this analysis. So what I'm saying is, instead of having this, I'm going to have a function of this. Okay? I'm really interested in modeling G of the expected value of y given x, such that I find a function, something, a G here, that may lead me to exactly this linear form. Okay? Beta 0 plus beta 1, etc. But note here that I don't have the disturbance anymore. So I need to assess the random part somewhere. And this random part is coming from the distribution of the dependent variable. when the dependent variable is dichotomous, poor, non-poor, what would be the distribution underlying these variables in statistics? Whenever a variable takes on only two values,
Binomials.
that's the Bernoulli process, right? Whenever we repeat the situation across the whole population, it is the binomial one. So the binomial is a repetition of a Bernoulli process. Okay, Bernoulli?
Yes.
Yeah, Bernoulli simply says you have only two values, 0 or 1, and 1 happens with probability p. That's it. You repeat that many times, and then you get a proportion, because you are summing up the ones. And then you get the binomial distribution. Okay, so we know it has to be binomial. So this length function has to be related to the binomial distribution in the case of a 0-1 dependent variable. And this is what I'm going to show you. So this is how we choose the length function. Okay? We choose it on the basis of the distribution that's characterized in the process. Here, a 0-1 variable, dichotomous variable, Bernoulli or binomial. Okay? So it's not something that comes from the sky. It's chosen on the basis of what is happening behind. Are we on the same page, all of us? Mm-hmm.
If we are assuming there is the randomness on the left-hand side by assuming a distribution, I mean, there has to be a mappable randomness on the right-hand side also.
It will be. There will be. There is a mapping there. And that's how it's explained, I think, in the book. In the book, I tried to add a section on estimation, quality of fit, and also a description of how the mapping is done. Okay? So this is our generalized linear model. Here it comes. So this is the basic dependent variables. Basic, I'm saying. This means that these aren't the only possibilities that you have. You may have others. We can begin with this binary variable here, right? Which will take a value of 1 if people, sensor deprivation score is greater or equal to k and 0 otherwise, right? In the case of a micro model. So the range of the dependent variable is clearly 0 or 1. The regression model would be a probability model. And then we need to decide on the length function here. Yeah? The length function, this g, would be the logit. So logit, I'm sure you know them. The logit is the model you use whenever you have a dichotomous variable as dependent variable. So you see that the logit is also a special case of the generalized linear modeling class of models. Okay? So this is the logit. We could also have the probit, so both are applicable here. Either the logit, which is taking the log of the conditional mean, which is the one I wrote here, divided 1 minus the conditional mean. Okay? So this is the length function. And then the mean function, because at the end we are not really interested in the log of the ratio. We are interested in the mean, in the conditional expectation. So we need to invert this thing. Right? Yes?
So, just to extend this, I cheated, I looked through your slides a little bit.
Okay.
So in terms of having kind of multiple bins, so we have a category, right, education or living standards and so forth, and then we have the different indicators.
Mm-hmm.
Has there been any experimenting using like a nested logit, so estimating a nested logit where you have individuals, and then also, of course, you addressed on your last few slides, fractional regression.
Yes.
And yeah.
Well, coming to nested logits, you will have two models, right? Nested, just to understand, we are having one model and then we have another model.
Yeah,
right?
within a model.
Within it. So it means that there is like a stage before where you have like a, let's say a probit, where you have 0 and 1. And within that, within each of those two possibilities, you're also having a second level where you have another probit. Let's say the probability of having education or not, and then having the probability of access to safe water. And then you would have this, both of them. So it's like a nested probit twice. You can also do that.
Yeah.
That would be interesting to assess. But it would be more on deprivation rather than poverty, because you would need the first indicator and then the second indicator. So there are other possibilities. You can explore other models. Just remember the type of variable that you are dealing with. That's all. That's my purpose here. Then it comes this one that we were talking about more at the aggregate level. We could have the M0 or we could have the H. right? M0, the multidimensional adjusted head count ratio or multidimensional index, and then H, the multidimensional incidence rate, right? What is the characteristic of both?
Between 0 and 1.
Yes, they are bounded. They are fractions, right? So these are fractions. That's why it says bracket here, fraction. So the model is again a proportion, but it's a model at the macro level because it's across provinces or across countries. And again, the conditional distribution here is the binomial process because it's a proportion. So both are essentially coming from the same types of distributions. So this means that we can use the link function applicable to both types of models. Okay? And there's also a paper here that is the one that we present at the end of the lecture, but also at the end of the book, where we discuss how we can estimate these things. Yeah, where we can estimate these models. Okay? Following Ulrich, I think, in 1986. Is this clear? This is simple. I'm just trying to explain the theory behind because it's one command in this data, as always. Yes?
I don't understand why you choose Logit in the micro level and not Probit, because...
No, both are possible.
Both?
Yeah,
Okay.
that's why this line here, it means that both
both
are
for
applicable
both.
either here or there. Both models are possible.
Okay.
But there's also, well, it depends on tastes, right?
Yeah.
But the Logit and the Probit are essentially probability models in both cases. According to your experiences, would you favor one or the other? If you use it, which one will you run? The Probit? Logit somewhere there?
If I want.
There is an equivalence. It means that if you run the Probit, the beta parameters that you estimate could be retrieved in the Logit form. So there is an equivalence between. But in empirical applications, you often use the Logit because it's easier to interpret. You need to remember that we are having probability models now. So these parameters that we had in the linear regression form, who would like to give me an interpretation of this beta 1 in the linear regression form? Marginal effect. So it would mean 1 unit increase of x here would lead to beta 1 units, I don't know, to increase in y. If both variables are written in log form, we're having the elasticity. Right? That's very intuitive and straightforward in the linear form. What will happen here? Look at it. It won't be the case, right? So the interpretation of these parameters is not as straightforward. And in the Logit form, we can have more intuition than in the Probit one. But both are equivalent. You will have results that could be reported in both types of models. So coming back now to this main case, the basic one, we have our dependent variable, which is 1 if poor, 0 otherwise. We are interested in modeling the conditional mean, we said, which in the case of a binary variable, the mean is equal to
0.5.
Okay, that would be the max, but the mean in a case of a dichotomous variable, the mean is equal to how much? The average. The average of a dichotomous variable is equal. If you type in data, what command do you use? Summarize. Okay, the summarize will give you what? The mean. The mean is a proportion. Okay, so that's why here I have the probability. No? Instead of having expected as it's written here, now it's written in probability terms. Right? So it's the probability of y given x, and we denote it well. Mu. So for this binary model, clearly we are using the Bernoulli distribution. Here comes the Logit. Yeah? So the Logit, we said, is the log of the mean divided 1 minus the mean. But the mean now is the probability, because it's a 0, 1. So it's the log of the probability of being multidimensionally poor divided by 1 minus the probability of being multidimensionally poor. So it's the odds, right? Odds. Being poor, non-being poor. Log of that. That is linear. That's what we wanted. Yeah? But we are not interested in the log of this. We are interested in these parameters themselves. Right? So what we need to do is to apply the inverse function, and then we get this relationship. We are interested in this path. Right? So how can we interpret the parameters? Here they are written in an additive form. Here they are written in a multiplicative form. Okay? So you have two possible interpretations for your models, and this doesn't only apply for the Alkire and Foster measure. This applies for any logit or product. Okay? So here you could have these betas, or the exponential of beta. So the interpretation comes here. Here. So we can have these partial regression coefficients interpreted as either marginal changes of the logit, log of the ratio, or as multiplicative effects on the odds. The odds is without the log. It's just the chances of being poor divided by non-poor without the log. Okay? The log of the odds is something else. So this beta j will indicate a change in the logit, which is the log of the odds, due to 1 unit increase in xj, more or less in the same way we have interpreted the linear model. And epsilon power beta j is the multiplicative effect on the odds of increasing xj by 1, while clearly holding constant the other explanatory variables. So epsilon power beta j is known as the odds ratio. Okay? So it's a ratio. That's different. And this is something you can compute either when you tabulate things. With dichotomous variables, you get the odds ratio as an option. Remember that despite you are using the tabulate command, which seems descriptive, behind there is a probit or a logit that is being run so that you can obtain the odds. Okay? So there is a model. And the model clearly doesn't have explanatory variables. We didn't give it. It's just a probit or a logit with a constant as the explanatory variable. So there is a model behind, even if you tabulate. So example, and this comes example. And this is a discussion, as I said, this is illustration. Okay, I try to do my best with this data set, which is the Indonesian one, trying to illustrate how to run things, and in a certain way, trying to avoid the endogeneity problem, because I didn't know what else to do. All the variables from the data set, we use them to compute the M0. We have an M0, which is in 5 dimensions, it's ambitious M0, have also education, living standards, assets, more or less as you are having. And then within each dimension, we have 3 indicators. Clearly, it's a rich data set, but we have used all the information in the construction of the M0. And then we were trying to assess profiles. Okay, it was much easier with profiles, but even if we're doing the profiles, the information on the household head was also included when identifying the poor. So we were having a problem there. That's why we are just using it as an illustration. It's not published. It's still being reviewed for I don't know how many times, but it's been reviewed. Okay? So here it comes, the Logit regression. We have the dependent variable 0, 1, being poor, non-poor, and then these are the, if you want, explanatory variables we included. We had a female household head, which was something we didn't use in the construction, so it was more or less okay, 0, 1, E female household head. Household size, okay, maybe. Living in urban areas, okay. And then being Muslim. So religion aspects we didn't include in the measure, which was we were okay. And here years of education of household head, where our indicator was if there is, as you have already learned, non-adult member illiterate. Okay, so which is not the same as years of education, but there is a problem there. And here we have the estimated parameters of the log of the odds, so the betas, with the standard errors, the T ratio, the significance level. And here we are reporting the multiplicative ones, which is already exponentiated. So here. And I have written the interpretation here, so that we understand. It means that estimated parameters exhibiting a negative sign denote a decrease in the odds. This is obtained, how do we obtain? As 1 minus the odds ratio times 100. For example, for the effect of education, that would be 1 minus 0.51 times 100. This leads to 49%. Okay? For the effect of gender, is the opposite. Okay, this is mechanic. You always do that. 1.28 minus 1 times 100, and this means an increase. And I always find it useful to have this, because whenever I read papers on probit and or maybe logit, I always get confused. I don't understand if it's a decrease or if it's an increase. Clearly, if you see the sign of the beta, it's clear. But when it comes to the interpretation, people move here. And they don't explain how they have moved from here to here. I'm not saying that you need to add a formula. You can just have a footnote on your papers saying one example, how you have interpreted those parameters. Okay? So this is a simple example of what you can do for a microregression. Yes?
If there is some kind of omitted variable.
See, and then clearly in any regression, you need to consider omitted variable problems or variables, right? And most of the time, whenever you have endogeneity, well, you use an instrument to estimate, instrumental variables, right? But there's always a discussion of how well the instrument is truly doing. Because for an instrument to be a good instrument, there's two things that need the instrument to fulfill. Is everyone okay with instrument when I say instrument?
It's very difficult to find an instrument.
Exactly. So the instrument doesn't exist actually. But the instrument needs to be highly correlated with the variable that you are trying to solve, to instrument, and needs not to be correlated with the error term. Okay? Instrumental variable comes whenever there is a correlation between this x and the disturbance of the equation. Yeah? Much as our colleague was saying, you were explaining the linear model, one of the assumptions of the linear model is that there is no correlation between this x and the disturbance. But in real life, we are confronted to something else, which is clearly a correlation. So to solve for this correlation, we find another variable that may come from somewhere else and try to find a solution for this correlation, to break this correlation. To break this correlation, we need this instrument, called instrument. Okay? But the instrument is very difficult to find. But if you have panel data, most of the time the instrument is the lag of the variable. Or alternatively, you can lag the variable. Instead of having the years of the education of the household head today, I could have the years of the education of the household head yesterday, the year preceding year. So you can lag things to decrease the endogeneity problem, just to make it smaller. The problem remains, but when lagging, the effect is not contemporaneous. It's not happening at the same time. Okay? That's also a possibility. But the instrument always remains as an option if you have a good instrument. So going back to this profile, what is interesting to retrieve from this data command, because the command for regress here is Logit, and then you run the dependent variable and the explanatory variables. That's it. You can get the predicted probability. Okay? So this predicted probability that I have here, I have plotted it by region, which is very interesting. As we have in design, the probability of being multidimensionally poor in the rural areas is higher, right? But decreases with the years of the education of the household head. Same happens for the urban area, but it happens at a faster rate, I would say, for the rural area at the beginning, and then both converge. Interesting to get, even from a non-policy point of view, I think from an academic thing, is useful. Okay, so let me finish now with a final slide, so you're free to go, which is, what do we do with this h and m0 as a technique? So clearly these are fractions, right? These are proportions. So we need to account for that. And the model for this is called a fractional model. And it's fractional in the sense that it's accounting the bounded. And what we do is to have a likelihood estimation, which is very different from the least squares that I have shown here, right? In this simple example, we had a line, and then we minimize the distance of each observation to the disturbance. That was the least square estimator. The likelihood estimator is an estimator in which we begin by assuming a distribution for the dependent variable, much in the same way as we are thinking now. So that's the likelihood. The likelihood is the probability of observing a sample. So because of that, we need to know what is the probability for that variable to happen. So here we are assuming a Bernoulli log likelihood, because the variable is fraction. Okay? So we use a Bernoulli log likelihood function. We maximize that, because instead of minimizing, we want to maximize the probability, and then we get the parameters. The code, I think, is also implemented in Stata for fraction. I think you need to look for fraction model, and the code will come out. It's one line also. Okay? So this is, I think, all I had to show you in terms of techniques. The chapter is an introductory chapter to regression, and I hope that in the coming years there will be more empirical examples with real problems, with real policy questions that we can add to the chapter when we revise it.